Welcome to This Explainer. Today, we're taking the invisible physics of sound and turning it into a highly visual, high-tech journey. We're going to pull back the curtain on those everyday sounds you hear all the time and really reveal the intense and, honestly, sometimes violent mechanical forces that actually make them possible.
So let's start with a bang. Literally. Think about a shattering glass. It's so easy to think of sound as, just a sensation in our ears, but it's deeply, fundamentally physical. Under the right conditions, invisible waves of sound can cause the wall of a drinking glass to oscillate so violently that its structural integrity completely fails. It just shatters into pieces. To understand how thin air can actually break solid glass, we've got to look at the underlying mechanics.
Okay, taking a quick look at our diagnostic menu to map out our progression today, we are covering 1. The anatomy of sound waves. 2. When sound waves collide. 3. Intensity and the decibel scale. 4. Resonance and standing waves. 5. The beat phenomenon. And finally, 6. Doppler effects and shock waves. Let's get into it.
Section 1. The anatomy of sound waves. Unpacking the microscopic mechanics. Let's start right at the source and define exactly what an invisible sound wave actually is.
You know those transverse ripples on a pond where the water bobs up and down while the wave itself moves forward? Well, sound doesn't work like that. Sound is a longitudinal wave. This means the actual elements of the medium, like the air molecules around us, pulse back and forth in the exact same direction that the wave is traveling. Imagine, say, a piston pushing into a tube of air. It compresses the air right in front of it, and then as it pulls back, it creates an expansion. That moving, periodic pattern of high-pressure compressions and low-pressure expansions, that is exactly what we hear as sound.
Now, check this out. The speed of sound dramatically changes depending on what it's traveling through. In room temperature air, it moves at a respectable 343 meters per second. But look at water. It leaps up to nearly 1,500 meters per second. And in solid aluminum, we're talking over 6,000 meters per second. Now, you might be wondering, wouldn't water, being way denser than air, actually slow the wave down? Well, the speed of sound is dictated by two main things, density and the bulk modulus. And bulk modulus is just a measure of incompressibility. Since water is far more incompressible than air, its bulk modulus is overwhelmingly higher. That absolutely makes up for its density, allowing the sound wave to travel much, much faster.
As this longitudinal wave moves along, it's defined by two interconnected variables. First, the displacement amplitude, which is literally how far the air molecules physically shift. And second, the pressure amplitude, meaning the maximum change from normal air pressure. Now, here is the fascinating physics secret. They are exactly 90 degrees out of phase. What does that mean? Well, when an air element is shifted to its absolute maximum physical displacement, the pressure variation at that exact spot is zero. And conversely, the moments of highest and lowest pressure happen exactly where the physical displacement of the air is zero. They're perfectly synchronized yet completely offset. It's like a perfectly choreographed dance.
Section 2. When sound waves collide. The mathematics of interference. Let's see how this builds when multiple sound waves interact in the exact same space. Because, let's be real, out in the real world, you are never just hearing a single, isolated wave.
So, here's the crucial question. What happens when you have two separate point sources emitting the exact same sound, perfectly in phase, but those waves have to travel different distances to actually reach your ear? How do these high-tech pressure variations combine when their path lengths differ?
It all comes down to the math of interference. If the difference in their path lengths is exactly one wavelength, or 2, or 0, basically any integer multiple, the waves arrive perfectly in phase. Their high-pressure compressions align perfectly, creating fully constructive interference. The result? The sound gets much louder. But, and here's the crazy part, if the path lengths differ by an odd multiple of half a wavelength, like 1.5 wavelengths, they arrive exactly out of phase. The compression of one wave meets the expansion of the other, and they mathematically cancel each other out. Fully destructive interference. That means two incredibly loud sound sources can actually combine to create total dead silence at a specific point in space. Mind-blowing, right?
Moving on to Section 3. Intensity and the decibel scale. Measuring acoustic power. This brings us directly to how we actually measure the raw power of these waves, the energy they carry, and how our own ears perceive them.
Now, human hearing is an incredibly sensitive, almost miraculous detection system. The very threshold of human hearing starts at this extraordinarily tiny intensity, 10 to the negative 12 watts per square meter. To put that into perspective,
At a faint conversational frequency, the actual physical displacement of the air molecules at this threshold is around 11 picometers. That is roughly 1/10 the radius of a single typical atom. Let that sink in. Your ear can detect variations in air pressure so insanely small that the air molecules are moving less than the width of an atom.
Because we deal with such an enormous range of intensities, everything from the gentle rustle of leaves to a roaring jet engine, we can't easily use linear measurements. The numbers would just be way too big. Instead, we use the logarithmic decibel scale. Basically, every time you increase the sound intensity by a factor of 10, you simply add 10 decibels to the sound level. And this brilliantly illustrates how ear protection works. If a veteran rocker wears an earplug that drops the sound level by just 20 decibels, they aren't just cutting the sound a little bit. Because it's a logarithmic scale, a 20 decibel drop actually cuts the raw sound intensity reaching their eardrum by a staggering factor of 100.
All right, Section 4, Resonance and Standing Waves, Confining Sounds to Create Music. We've talked about waves moving through open air. But what happens when we intentionally trap these powerful atom-moving pressure variations inside confined spaces? Well, this right here is the fundamental physics behind all musical instruments.
Think about a didgeridoo. When sound waves are pumped into an air column, like that hollowed-out piece of wood, they travel down to the end and are reflected right back through the pipe. If the wavelength of that sound is perfectly matched to the length of the pipe, the forward and backward traveling waves overlap, creating these massive sustained oscillations. We call this a standing wave. This is resonance. It literally allows the air to push back and forth with a huge sustained amplitude, emitting a really powerful musical note. But notice the strict mathematical rules governing this resonance, all based on the shape of the instrument. If a pipe is open at both ends, kind of like a flute, it must have a node, which is a point of zero pressure variation, across both open ends. Mathematically, this allows the pipe to produce any harmonic frequency, the first, second, third, and so on. But if an instrument is closed at one end, like our didgeridoo, that closed end acts as a hard boundary. It forces a physical displacement node right there. This mathematically restricts the pipe to producing only odd harmonics, the first, third, fifth, and so forth. So, the physical shape of the instrument literally dictates the mathematical formulas of the sound it can even produce.
Section 5. The beat phenomenon, when frequencies mismatch. Now, things get really fascinating when we introduce waves that are just slightly out of tune with each other.
To ground this math in reality, we have to ask a behavioral question. How do emperor penguins locate their specific mates in the harshest, loudest, most visually confusing environment on Earth? They all look absolutely identical, and sight is pretty much useless in a howling Antarctic blizzard. Well, the answer actually lies in their throats. Unlike most birds that only use one side of their vocal organ, emperor penguins vocalize using both sides of a twin vocal organ, called a syrinx, simultaneously. This effectively acts like two distinct air pipes, allowing the penguin to set up two acoustic standing waves with slightly different frequencies at the exact same time. So, when these two slightly mismatched frequencies meet in the air, they interfere with each other, moving slowly in and out of phase. Let's say one side of the syrinx produces a 432 Hz tone and the other produces a 371 Hz tone. They combine to create what's called a beat frequency, which is literally just the difference between the two numbers, in this case, 61 Hz. This results in a slow, wavering variation in intensity. The penguin is essentially generating a complex acoustic barcode that cuts right through the deafening noise of the flock, allowing its mate to mathematically pinpoint its exact location. Section 6. Doppler effects and shock waves. Extreme sonic movement. Finally, let's push the physics of sound to its absolute limits by examining what happens when the source itself is moving relative to the air.
You've probably heard of this one, the Doppler effect. As a sound source, like an ambulance siren, moves towards you, it essentially chases its own sound waves. This bunches them up and decreases the wavelength, which you perceive as a higher pitch. But once it passes you and speeds away, those waves stretch out, and the pitch drops dramatically. It's a perceived shift in frequency based purely on relative velocity.
But what if a source accelerates so much that it completely outruns its own sound waves? When an object exceeds the speed of sound, like a supersonic jet, the spherical wavefronts literally can no longer escape ahead of it. They bunch together, overlapping perfectly to form a massive, concentrated wall of pressure called a Mach cone. And when the edge of this cone sweeps over you, you experience a sudden, violent change in air pressure. We call this a sonic boom. And hey, it's not just for fighter jets. When you hear the sharp crack of a bullwhip, you're actually hearing a miniature sonic boom because the very tip of that whip has broken the sound barrier.
So the absolutely crucial takeaway here is that sound is not just some passive experience. It is an active structural force. If these invisible variations in air pressure possess the mechanical power to shatter solid glass, guide biological life in the Antarctic, and literally crack the open sky with sonic booms, what other incredible, invisible physics are quietly shaping your world at this very moment? Thank you so much for exploring the mechanics of sound with me in this explainer. Keep questioning the invisible forces around you